Okay, anybody knows that? Please? Okay, a lot of people. Nice. So that's a tomato. Okay, no, that's that's a Pomodoro. It is 25 minutes. And what is Pomodoro is a management of time, because we lack time, and sometimes we need 25 minutes to do things. So just I will do that. 1 hour is just 25 minutes. 5 minutes to rest. Okay, I will sleep, or maybe answer questions, and then 25 minutes, and we'll finish with questions. That's the Pomodoro technique. You can see it on this website, and this is something that I use for my lecture, because my students, they are on computers during 4 hours, and 4 hours is too long for them. And so we are playing with Pomodoro. We are developing coding during 25 minutes, and then we will take a coffee and things like that. And let's again and again during 4 hours, and it works really well. So let's begin. 25 minutes. Okay, here. Okay, I'm Jannik Laval. I work with Nouribo Akadi and Luc Fabres, and we just a small talk with robots. We are working in France at Douai. I'm happy to be there today. So our research is about software engineering for robots. So it's not about electronic or automatic or other things. No, it's just software. So what is a robot? It's kind of that. Maybe, or not. It's a really, really long-term goal, because robots now is this kind of things. Okay? This is a vacuum. We can see these kind of things at home. And this is the NASA robot that is on Mars. Okay, this is the only one that are not produced in series. Now, at our lab, we have some kinds of robots. We have those robots that are Wi-Fi bot. They are just one Wi-Fi connection, 2 motors, and 2 infrared sensors. And you play with them by sending command by Wi-Fi. That's all. We have also turtle bots. They are like that. This is a base of vacuum, and we build layers on top, and we can put a computer to control the robot, and you can put Kinect. Like that, you have really good sensors. You can make 3D sensors, 3D views, and things like that. So it's pretty cool. It's 2,000 euros, so it's not so expensive. And we have this kind of robots. This kind of robots is I like that. And okay, they have lots of sensors and good motors. There are 2 motors and sensors. We have a laser. We have 10 or 12 infrared, and also sonars. So they are really, really great. We have 2 cameras also, one there and one there. We have an embedded computer. This is Windows CE operating system, and we have another computer here to manage the robot. So, okay, that kind of robots are really different. Okay, we have a computer here, we have a computer here, but here we have two computers, one here, one inside. Here we have only one computer, here we have nothing. Okay? Okay, but the infrastructure is the same. Infrastructure is, okay, you have your physical environment, you sense it, and you send it to a computer. Even in case of Wi-Fi bot, you are sending information by Wi-Fi, so it's the same. And then you are managing this kind of information on the higher level, that is software. So we do this kind of things. Okay, we are working there, not there. So here we are doing that with Faro. That's all. So that we have multiple problems because I show you 3 kinds of robots, but there is multiple kinds of robots. You have flying robots, quadrimotor robots, maritime robots, and other kinds of robots. And you know probably there's kind of robots also, humanoid. We have 2 of them. And okay, this is just for playing. This is really expensive for playing, but this is just for that. Okay, you have this kind of robots also. And okay, you have to manage heterogeneity. Heterogeneity is about different sensors and actuators. They are about different computing capabilities. You know, this kind of robot has better performance than this one. Okay, you have a bigger computer inside. You have also different drivers and protocols because they are made by companies that made their own protocols, and okay, you have to manage that. And you have different low-level algorithms, and you have different shape and size. Okay, that's crappy. So, you know, implementations exist. Oof. Okay, there exist in C, C++, and Python. So, yes, but we are working with Faro. So now, how we can manage that to continue to work with Faro, with our language, and to discuss with that. The idea is to use middleware. The middleware is used to manage the information from this language to the computer, to the robot. And the main one is ROS, Robot Operating System. So, okay, we want to discuss with ROS. That's why we built Pharos. So let's talk about Pharos. The main goal of Pharos, the first idea is we had a project that is a robot guide in a shopping mall. But it can be used in a museum, in a hospital, or other things. And, okay, you know him? It is Santiago Bargagnolo, he's Argentinian. And he works a lot on Pharos. He's the main developer, and you see the robot is here. And, okay, he made a lot of work on Pharos, and we can do this kind of things. We control the robot with Pharos. Okay, it's 2 times speed because you know, we are in a corridor that is a bit low. So, and the robot have a preloaded map with point of interest, and you can say to the robot, okay, go there, go to this office, and the robot is moving to the office, and That's pretty cool. Okay, when they are localized, they can they follow the shortest path, and this kind of algorithm is not done in Faro. This is the part of ROS, because we don't want to reinvent the wheel. There is a lot of robotics guys that work on algorithms and mathematics and things like that. So we don't care. We just want to use the things. Okay, we can control the robot using a navigator, an internet navigator. Okay, that's just made with Seaside, because Seaside is inside Faro. And just let's go, and he moves. Okay, let's appreciate this video. And you can see that the robot can wait, or they can avoid other things, and all is controlled by Faro and Pharos. What does it mean? It means that okay, the main software is outside Faro, clearly.
Yeah, but it's like the mathematical algorithms or the libraries of Faro worries about the level.
Yes, this is what we want. Yes, this is what we want, because ROS is a kind of okay, it's the model is processes. You have processes that communicate between them, and okay, you want to manage those processes, but when you want to change a parameter or something like that, it breaks all the things, and we want to manage that on Faro dynamically. So this is the map that we have. The map is okay, it's the map of our building, and it's made by the robot itself. It means that we have, okay, in the demonstration I said that the robot has a periodic map. Yes, but this periodic map was made by the robot itself. And okay, we have some algorithm for that, and the robot moves inside the building and it builds the map. And you can see that there is some artifacts like that. They are just doors open or window or things like that. So we can pay attention to that and to remove them. So we don't care for this demonstration. And then we just have inside Faro to have annotated map. We just put the point of interest, and okay, that works. So what is the architecture? The architecture is, okay, we have Pharos, we have the robots. The robots is, okay, a lot of things, and proprietary software. That's important, because each robot has its own software. That's terrible, but it's the case. And we have, at the other side, ROS. And in ROS, we are using Path Planner and localization service, localization system. And okay, whoops. We are putting Pharos there. Pharos is here. We have a bridge to control the software, the robot. And this bridge, we build two bridges. One for the Robilab and one for the Lego Mindstorms. Like that, we can control them with Pharos. And Pharos will communicate with ROS. And on top of that, we have the Seaside application that allows us to control the robot on the internet. The thing is, inside Pharos, this is not just controlling ROS node. We can build inside ROS node. Like that, we can have a dynamic system inside Faro, and that's pretty cool, because for the Robilab, video that I show you. Okay, we have the bridge, and we build ROS inside ROS nodes inside Pharos, and we send the command to the main middleware. So that's cool. We can talk to robots with Pharo. We also can talk to robots with Pharos. This is better than Pharo because we are using a great middleware that is the main middleware, and that is used by everybody now. So now, we can talk to robots with Frach. Do you know Frach? No? Okay. Frach is visual programming for robotics. It's not on top of Pharos, but we can do it. So what is Frach? Frach is a kind of Scratch, but on top of Pharo, and first on top of Pharo and dedicated to robotics. So, you know, this is Scratch, okay, on top of Pharo. This is based on the SCAT project. We merge all the things. Okay, we win the SU 2013 third prize. And we have a website, frach.com, sponsored by SU. So thank you, SU. Okay, there is a lot of movement with Frach. We have the website, we have smart icons. Okay, beautiful icons. We have Jenkins, that works really, really well. We have the image, the one-click images, and we are trying to build something on Raspberry Pi. Okay, it works. Okay, it loads on the Raspberry Pi. Yes, we have a lot of problems with. Okay, it's a small processor, so we have lots of problems. We discussed a lot with Tim Rollege about that. And we have the Jetstorm Robotics that won SU 2014 in Cambridge, the second prize. So what is interesting in Frach is you can build add-ons. It means that you have your software or robotic software, and you want to use Frach on top of it. You can just build an add-on. It's really simple. I will show you that just after. So we want also the code accessibility. Why? Because when you are doing some blogs, that's great, but some students asked me, I want to see the source code. I want to understand what is beside that. Okay, for now we have a kind of algorithm that is available also in Scratch, but the next step is to make it in Smalltalk. So, and then you can just click on a block and show block, and you can see the real Smalltalk. That's for the users. And then if you want to edit a block, you can do it because it's your system. So when you click on it, you see you have the browser, and you can see the method. And what is interesting in this method is, okay, I have a signature, I have the content of my method, and I have two things here. The first line is a command. Whoa. No, that's not just a command. With this command, we can build documentations. Because inside Frach, just on the help menu, you can just go to generated documentation. It takes all of that and build an HTML file. and that's just easier for users. And the main thing is this line. So everywhere inside Faro, you can put this line. Not really everywhere for now, but it's for Fratch 5. But for now, we just have to subclass this class and put it inside your method. And this line, this pragma, is just to declare that. So everywhere in your system, you can just put this pragma and you have this kind of block inside Fratch.
That creates the blocks automatically for you to use.
Yes, that's automatic. And okay, that's Fratch item. You have the definition, move, numbers, steps. Okay, move a number and steps. And this is the kind, it's a command block. This is the normal kind. You have also booleans, return blocks, things like that. There is the category where you want to show the block and a default value and a subcategory, why not? And special is just a method that you want to execute before the block appears. Okay, it works. Again, Jetstorm is Fratch, but for Mindstorm. Okay, all of these things are made for Mindstorm. We have the bridge that I explained to you, and you can control the robot. You can control the motors, the sensors, but the screen also, and the LEDs, the sounds, just with Fratch. And it is used by our students. Okay, you can see we are using Scrums.
Is Fratch running inside the robots?
No, it's just control. You see, there is Wi-Fi key. Why? Because it's an ARM processor, and we have to put Faro inside. Okay, we can do it, but we need time, engineers' time, and things like that. So here you can see there are students are playing, and the goal of this course, of this lecture, is to learn robotics. So learning robotics is I need to know about robotics, about motors, about sensors, about data, about automatics, about electronics, and about programations. Okay, our students does not know anything of that because this is just their first year, so they don't know how to program, and this is why we did that. And they are doing path planning, they are doing labyrinth solvers and things like that, just playing with Mindstorms and Fratch, and they are doing really great things with that. And you can, so this was the source code, because you can control it with Faro. And what is exciting is that when you control it with Faro, you can inspect your robot. That's an object. Yes, that's an object. So it's a real object, but that's an object. And you can inspect it and play with it at real time. That's our goal with Faro. The main thing is to say we are living in a dynamic world. Robots are dynamic inside a dynamic world. We have to control them with a dynamic language. It makes sense. So, 25 minutes. I'm okay. Okay, for all the guys that does not know about Pomodoro, you made your first Pomodoro. Okay, I have. Yeah, we can take a coffee or leave and or I can answer questions also. Yes.
Have you tried to maybe this is a crazy idea, but have you tried to generate code while you are controlling the robot? I mean, because it's a dynamic world, and maybe if you create a few rules, and I don't know, just thinking if it makes sense or not.
Yes, it makes sense. When you are saying generating code, is
I mean, for example, you have a robot and you only tell him that he cannot crash against the wall, or, and with few rules, then put him a code and see if he can do it dynamically, and I don't know.
yes.
Have you tried those things?
Okay, that's the following. Another question, because I cannot answer that. Yes.
First, as a word, you are doing such an interesting and exciting point, to an exciting direction too.
Thank you.
So, congratulations to that. My question is, are you guys thinking, because you are having experiences of how to teach with that, right?
Yes.
So you are the kind of the first one, or you are kind of trenches. And my question is, if you are thinking on passing these experiences to other educational institutions or efforts, because, for example, I know in Brazil, Scratch is like, people is really excited with it.
Yes.
And there is activity. And maybe they don't even know you are doing this, and they will be going, wow.
Yes, just make advertisement for that.
Okay, I could make you an introduction. I know
Yes.
the girl that is
Okay, that's a good point. That's a really good point. We will be happy to yes, probably to travel to give a lecture or something like that. I don't know about Brazil.
yeah, it's more boring than that. but it's exciting.
Yes, we can give lecture or things like that, or just give documents, or just
Exactly.
that's yes, we are open with that. Really.
Yeah, I will try to connect.
Yeah.
Right.
Thank you. Okay, one last question. No? Okay. Let's go. So, begin with the second Pomodoro. We have more challenges because, okay, we are playing with robots. We have a robot that is in a shopping mall. Now, what is the goal of a robot? Is to go there. Because in kind of earthquake, or maybe Fukushima catastrophe, and you don't want to send human there. You want to put robots and do the job. And here, this is really difficult because we have changing conditions. This is outside the robot. Okay, you can have a map, okay, because you have Google Maps and things like that. But here, Google Maps is useless because the conditions have changed. Then you have problems of resource because if you put a robot there, if you have no more battery, okay, you lose your robot. And this is the kind of battery, but you have problems with CPU and RAM and things like that because the robot has to compute all the things. And you want also an integration of hardware and software. For now we have the hardware and we put the software on top, and we want more integrations. So, for changing condition, we want self-adaptation. This is not the case of this presentation. I will do the two other things. Why? Because we are working on that. About resource constraints, you want, smalltalk plus FPGA. So you know FPGA? Okay, it's a great processor that you can rebuild at runtime. So we have an experiment that, okay, just build a Faro robotic application and identify critical parts, and then project the critical parts on FPGA. Okay, and okay, we want evaluation of performance, but you know, in robots, for example, on video processing is really hard to do because we need a big processor for that. But we can do that on FPGA. Yes, but we need knowledge about FPGA, about VHDL, and okay, it's kind of crappy to develop on that. The idea is probably I can create my software in Faro, in Smalltalk, and just take some component and push them inside the FPGA. Okay, we have a PhD student on that, so we have not the solution. This is just experiment for now. So we did the experiment. The robot should follow an object using a color pattern. This kind of experiment was made with this robot, and the camera resolution is really low. So we have to detect the object. You can see that you have the robot and you see the ball, yellow ball, and the robot is moving. But you see the video is really low quality. And sometimes, okay, you lose the ball. And you see the processing time per image is 650 milliseconds. That's why it's so low. That's so slow. That's just incredible. So we have this kind of process. We have the camera that sends RGB file, and we change it in HSV, and we have an HSV filter, and we have an object detector, and we have the laser sensor to locate the robot, and then we send a command to the robot. Okay, the critical part is here about the image processing. That's clear. And okay, the idea is what I said is, okay, why we want to do a Smalltalk application and send it to a process that make partition of hardware and software, and then send it, make process it a part inside Faro and another part inside FPGA. So it works. When I said it works, we made that manually. It's not at runtime. The goal is, okay, I want to do that inside Faro. Manually we can, okay, select some part of source code and push them. But what we want to do is to make it automatically first, and then at runtime. Because sometimes you have problems with images, but sometimes it can be other things. A lot of data that are received or things like that. So you want to change the behavior of the FPGA at runtime. And this is the goal of this PhD. We hope a lot for that. Okay, another things. Hardware and software integration. I want to talk about TDD, test-driven development. Why? Because when you are in this architecture, you are doing robots, okay? You know that the actuator works, you know that the sensor works, and your computer works. Your software is working also. When you plug all the things, the robot does not move. Okay, I'm happy, but everything is working. What happens? And in the main case, okay, it cannot move, but it can break something, because it can move on a wall and break or the wall or itself. And so we want safety. And for that, we want to test the robot. And to test a robot, you can do simulation. The first step is to do simulation. Simulation allows you to test your software on a simulated robot. Okay, this is something that we are doing too. We are doing multi-robot simulations because why? Because we don't have enough robots to make that for real. 8 robots, but we have 30 robots inside the simulator now. And okay, you can see that robots are moving and your software is working well. And they are building maps. Okay, all is done in ROS. So we can control that in firewalls. But simulation does not take care about noise. Okay, you can put simulated noise inside your simulator, but it's not the real noise. That does not take care about resources, about failures, about asynchrony and precisions. All of that are parameters that you can change in your simulator, but it's not the real life. So we created a methodology for safe TDD for robots. And the first things to do is to ensure the emergency stop. That's the first thing. Before using your robot or moving your robot, you should be sure that you can stop it. That's all. That's the first test to do. And then you will order tests. You don't want to test your robot that is moving well and blah blah. And no. First of all, you will test your sensors. Test your sensors, and when your sensors are working well, you test your actuators. And this is the same for 2 other things. You want to test your robot in a controlled environment before an open environment. Okay? You put your robot in a box and you see what happens. And then you remove the box and you try it. And this is the same for static environment and dynamic environment. The first thing is to try it in a static environment that you know that in a static environment the robot should move 1 meter, it moves 1 meter. In a dynamic environment, if you want it moves 1 meter and there is something that happens, it should do something else. This is not the same behavior, and this one is more complicated. So it means that you can order your test and preconditions your test. It means, okay, ensure that the emergency stop works. Then you try your sensors in a controlled environment and static. This is the second step. Then you will try your actuators in a controlled environment and static one. And then your sensors inside an open and static. And you can build your test like that. And you have 2 prerequisite tests. It means that all these tests depend on this one. And each time these tests are executed, this one is executed before. Okay, we have a framework for that. This is BoTest. It's available on Smalltalk, I think. And it's pretty cool. I don't have the source code here, but you just have to make inside the test self-prerequisite and a symbol that is or a class or a method that depends on your test. So it works fine. Okay, you know, the future is robotics. A lot of presentations during the 3 days are saying that the future, the next future, is about smart objects, connected objects, smartphones, things like that. But we are sure that after that, we'll have robots everywhere. When I say everywhere, it's real. We have more than 10 million robot vacuum already in the world. They are robots. They are moving alone. And they are doing things that humans do not want to do. And, okay, that's the real world. But, okay, about robotics. You know, Amazon drones. Okay, Amazon is playing with robots. Okay, that's a small company. More, again. Google is playing with robots, with self-driving car, but more like that. Google bought 8 robotics companies. Okay, they are playing with that, and they are doing great things. So, I am sure that the future is robotics. Just let's make it with Smalltalk. Smalltalk is a great language. It's a dynamic language. And it's a dynamic environment. You know, robots is, again, it's dynamic. In a dynamic world, we can control them with Smalltalk. Just like me, the future is Smalltalk. Okay, thank you. A last thing. Do I love Argentina?
Oh, hey. But why?
Okay, that's the question. Okay, you have a small country, that is Argentina, but there is a smaller one, that is France. And inside this small country, you have a small city, Douai, that is here, near Lille, and you know Paris is something like here. And inside this small city, you have a small office where we are recruiting Argentinian. So why we are recruiting Argentinian? You know, we had already a lot of Argentinian here. We have Guillermo Polito, we had Mariano Martinez-Peck, we had also Santiago Bragagnolo and probably others. I cannot remember all Argentinians guys that were in this office. So why we are doing this advertisement? Because Argentinian guys are really great. And they are really great, first, because you are thinking well, and second, because you are doing small talks. That's interesting, because in France, we don't see any students that want to do small talks. So we are recruiting for master thesis, master students, PhD students, engineers. We don't care, but if you are interested to visit France or Europe, just apply. That's all. Thank you. Okay, the second Pomodoro is not finished, but my presentation is finished, so we have more time for questions. Okay, questions? Yes?
We live in a dynamic world where you have like a lot of sensors, and you receive data parallel from all the sensors.
Yes.
How do you deal with that? With model is not parallel.
You know, parallels information in ROS is not real because you have multiple nodes, and if you have to manage this kind of information, there is only one node that manages that, and it means that all data arrive not parallelly. That's not a problem for us. So we have just another node, and we can manage data. Now the data are time-stamped, so we can do things with that.
I would like to know your vision about the impact that robotics will have on software development. So imagine you have software in devices. You have also what about change? What about version? What about
Yeah.
variation? What's the impact? How should we enhance our management?
Okay.
We want
That's-
to address.
That's a really open question. And okay.
Without skimming.
That's one point is when you are doing software engineering, in case of normal development, you are developing your software, compiling it, play it, and that's a short path. Now, in case of robotics, it's the same case as telephones or things like that. You are doing software, you are compiling it, you are pushing it inside your device, playing it, debugging it, come back in your computer, lose your context. Yes, lose your context. And just read software code to trying to understand your bug. And then, okay, you understand, you're recompiling it, you push it again. And this is a long path, this is a long way to every time have, oh shit, I have a bug. Again, okay, come back in my computer and what happens? And okay, I have to push it again. And okay, one thing, we had a student a few years ago that worked on this kind of problem, and he pushed a Faro VM inside a phone, and he can control Faro with his computer. And okay, if you can manage that, you can develop inside your computer but on your robot. And this is the way. But this is the way for robotics. This is the way for all devices. We are not developing inside our computer. We will not develop inside our computer. We will develop on other things in the cloud. There is another question, and then
It's a very great question.
yeah.
You said that you are splitting the software and what you want to put in the FPGA.
Yes.
I remember there was some work that line.
Yes.
I think it was Loic.
Loic Lagadec, yes.
Is that what you're using? How do you translate the code into FPGA, or is that manual? You have some option to choose.
Yes, for now it's some option that we push. For now it is not a real small talk code that we are working. Now we have to abstract that, and we are thinking that it's possible. So yes, we are working with Loic on he's the PhD director of the guys. Yes.
I guess I'm going to ask probably a simple question. So if I take a device like this,
Yes.
wouldn't you say this is a robot? It's a robot that has a rich set of sensors, but it has a very poor set of actuated devices. It can shake, it can vibrate, it can flash lights, so it can't move or interact very much, but it has lots of sensors and stuff in it. And so in one sense, what we really have is like sort of continuous spectrum devices in the ambient computing world, where at one end you have sort of fixed computers that only communicate communications lines. At the other end you have very mobile computers with lots of sensors, lots of ways to interact with the world, but there's a whole spectrum between the two, and much of what we do is software development. And the skills really need to translate across that kind of spectrum. I'm sure you
Yes, you're right. This is probably a kind of robot, but you know, robots can change their environment, and this device cannot.
Right.
That's
Well, it can to a limited degree, but some robots can be like a mist thermometer, right?
Yeah.
It's sitting there sensing the world and changes the environment.
That's okay.
Thank you.
Thank you.